one thing while I'm thinking about it, so you know how that first part of the lab didn't work for anybody? So I had somebody come in last night and it worked every time. Every time. Yeah, don't ask me. So I went over there, so I said, hey. So I went over there when he came in and I said, hey, let's just hurry and I'll show you what's supposed to happen here. And I mixed them and I'll be damned if they don't work. I'm like, that's crap. So I said, hey, you do it by yourself now. Sure enough, they all worked. Yeah, I don't have I have no idea. I was pissed. I'm swearing. I'm like, whatever. So go figure. So yeah, I don't know what, because I still have this one right here. Nothing. Got one on my desk. Nothing. I did it like 4 times. Mixed up brand new chemicals. Did it again. Got nothing. He comes in. Bam! There it goes. Like, piss me off. But I don't know. So we'll see. Alrighty. Now we are going to start chapter 7. So I believe it is the 16th today, right? Yep. Alrighty. And this is 6th period. Now while another thing I am thinking about, now, the only time, okay, you can do a lab with the video is if I can document that you are physically quarantined. Okay, so the college is really being picky, if you will, because of all the cluster that's going on everywhere. So, like, Dab emailed me last night, and he's cleared now. So if you're here, you have to do the lab physically. That is the one thing that they are really, really crazy about. Now, if it's a situation where you're going to be out, then there's nothing we can do about that. You know, but if you're just absent, I have to be able to physically document that you were quarantined for you to be able to do the lab by the video. Did you dye your hair? Oh, okay. Like it. Sorry, just noticed that. Did you have it dyed the other day?
No.
Oh. See, I'm not like most guys. Yeah, I noticed that. Did you notice that, Geddes? Oh, did you say something about it? Dude, come on, man. You're falling down on the job.
All right. It's shorter too?
What?
You notice that it's shorter?
Yeah.
Okay.
Yeah, but I didn't want to point out too much. You know, just a little bit. You want to let them know you noticed, but not, be over, over the top.
So it takes my grandpa 3 weeks.
Oh, yeah. No, it's bad. I'm married. I know that. It's like I was telling my last class, I'll do something and I'll get yelled at, and then I'll do something else and I'll get yelled at again. I'm just like, whatever. Alrighty, so our objective is going to be able to better understand gas laws. Now, This chapter is a little bit different in that there's going to be way more math. Okay, most of the recent chapters has been pretty much just like, if you look at the last chapter, it was like 70% you just knew the answer, you didn't know the answer, right? Now there was some conversion math, but by and large that was maybe 20% of the test was all. Is there somebody over there? Can I help you?
I was doing a test.
Oh, so you're the one, Mr. whose class?
Pollard.
Oh, okay, just checking. I got that email. I was just making sure you were going to tell me the right place. You didn't pass somebody in the hall and they said, hey, just tell them, Nobody knows it. Nobody's ever done that before? No? I get it all the time from seminary. Oh, I was in seminary. I'm like, so? That's God's time. This is my time. Whatever. Alrighty, so, 3 states of matter. And that's of matter, not that matter. What do we got? Solid, liquid, gas. What can you tell me about them?
Solid, highly organized.
Highly organized. That's good. Highly organized. And that's important because they're going to show you a situation, and I believe this is actually a good test question to bring up. When they get to this, there will be some artwork questions. You guys all know what I mean when I say artwork, right?
Maybe like the particles close to
Exactly. And there's a good, maybe it was in a different chapter, but you guys know the one I'm talking about, where they're going to be very close together, but they're both close together in a solid and a liquid. The difference is that in a solid, they're organized. They have a very definite repeating pattern. It must not be in this chapter. I'll see if I can find that picture. I know it's in this book somewhere. Okay? Okay, so highly organized. What else? There's two other things we've already learned about this. They have a...
Definite shape and volume.
Okay, what did I call that? Remember what... Definite's way too long for me to write. Fixed, right? So we went fixed, shape, and volume. Okay? What about a liquid?
Variable shape.
So it is variable shape. So it's got variable shape, but it has a fixed volume. Okay? And if I was gonna compare it from a solid to a liquid, if a solid is highly organized, a liquid would be what? Yeah, I would say less organized. I can't think of a really good word to put there, but yeah, it'd be less organized than a solid, right? Now a gas is very, very random. Okay. What about the other two?
Variable.
Yeah, variable shape, and variable volume. Okay, gases obviously take the shape of their what? Take the shape of their container. What's really important that you understand is this: if my hands are two molecules or atoms in a solid, do the atoms or molecules move?
Yes.
A little bit.
They actually do, a very slight amount. They say they vibrate, okay? So they're vibrating in position. The reason they're vibrating in position is from a couple of things, but usually is because the forces that are holding them together are strong enough that they keep them from moving, right? Now, as soon as I become a liquid, now those molecules have enough energy to do what? Now they start moving, okay? And the reason they're able to move is because now they've absorbed more what? Energy, right? We usually do that by doing what to it? I what? I heat it up, right? Ice, liquid water, right? And then I put enough heat into it. Now they're going to overcome those forces, and now they're going to do what? Now they're going to completely separate. And that is when that water molecule is now going to go from the liquid stage to the gas stage, okay, or the gas phase, okay? And that's what's going to happen there. I'm going to assume that this is all stuff that we probably, or at least hopefully, already knew, okay? Would that be a fair assessment? All right, okay. Now, gas pressure. Anybody tell me anything about gas pressure? What it is, how it occurs?
The gas collides into the shape of the container.
Okay, yeah. So what happens is gas pressure is basically a measure of the force of the particles colliding with the container wall. Okay? So right now, like here's my water bottle, right? I mean, clearly, this water bottle doesn't have very much what? Pressure in it, right? So I can do all this to it. And I don't know if you've ever noticed, but especially in the winter, you know, you'll be driving somewhere long, and if you're like me, I've always got 2 or 3 water bottles on the floor of my car, right? Well, as my defroster heats it up, what do you start to hear? Nobody's ever had this happen before. Yeah, I'm driving down the road one day and I start to hear these pops in my car, and I'm like, what in the hell is that, right? I get looking around, and on my passenger floor is a water bottle, and it's starting to heat up, and as it heats up, it exerts more what? Pressure, and as it exerts pressure, it starts to pop out all those little creases that were in there from it being stepped on. You know what I mean? And it pops and it creaks like that, right? I heat it up too much, what's going to happen? Yeah, it's going to pop the top. So, funny story. I used to work for a concrete company. And if you ever want to get an education, okay, go to work for a concrete company. Because it'll only take about 3 days, and you'll think to yourself, I need a different job. I'm going to go back to school. And I had never, I grew up on a 300-acre horse ranch. And I've worked since I was 8. Because that's just what you did, right? My father never, ever acknowledged me as having a job until the first week I came back from pouring concrete. We lived out of town. We built water tanks like that. Went over by the park, the big concrete one. We built them. Only that's like a 200,000-gallon one. We built like 3 million-gallon tanks. So we're talking as big as Beapod. They were huge, right? And I'd never forget, I came home. I laid in bed the entire weekend. I was so tired, okay? But anyway, we're driving to a job. And I was always the driver because I was the only one on the crew that didn't get plastered the night before, right? And so it's like 4 in the morning and we're headed for the city. And I thought, I'm not going to make it. So I bought me a 6-pack of Coke. I remember his old cherry Coke. They came in these light blue cans. Without even thinking, I put it on the dash, right? I'm on the freeway. I'm on I-15. Next thing you know, my cab is just full of pop. My defrost had done what? It heated those cans up and they literally exploded as I'm doing 75 down the freeway. Right in front of me. Pop everywhere. I can't see crap. I'm pulling over. People in the passenger seat are waking up going, what the hell? They thought we were under attack, you know. And I'm like, what? And then I'm like, oh my gosh, I'm an idiot, right? But yeah, I'd had the defrost on and I literally took those cans and they just blew up. Okay, so that's what happens. Now, you do need to understand this, though. Let's say I take this same bottle and I put it on the floor of my car and I leave it there overnight. What's going to happen? Yeah, Iverson. It's going to do what?
Really cold too.
It's really cold, so it's going to start to shrink down. Does anybody know why that is?
Expands colder.
Yeah, but why? You're right. Does anybody know why that is?
The particles get closer.
What?
The particles get closer together.
Okay, the particles get closer together, right? Because as things cool down, they move what? They move slower, right? As they move slower, they start to what they refer to as coalesce. Coalesce means to like coagulate, to come together, right? So as those particles move slower, they start to move together because now I've got what are called intermolecular forces holding them together. Now they're not colliding where? They're not colliding with the outside of the container as much, right? Or with near as much force, which means now the pressure on that container is starting to go down. And it will literally shrink and shrink and shrink and shrink and shrink. Now, the exact opposite is if I heat it up. Now those particles are moving what? Faster, right? Now they're starting to spread out even more. Now they're colliding not only more frequently, but with more force. And that's when my pressure builds back up. Okay, when I was a kid, I'll never forget this. My uncle taught me a lesson when I was like 8. And I remember we were playing, my cousins put in a basketball court. And I was not good at basketball, but we were over there playing one night and having a good time, and we all went in, and we lived right next to each other. So we go back out the next morning, and we're trying to play basketball, and the ball just won't dribble. And literally my cousin says, somebody let the air out of our ball. You know, and I'm like, jerks, right? Well, what happened? Did somebody really come along and let the air out of our basketball? So why wouldn't our ball dribble anymore? Richards.
The air on the inside was cold.
Exactly, because overnight it got what? Obviously cooler than it was the day before, right? So during the day, that ball was nice and bouncy, right? But overnight, it always cools down. So the ball naturally cooled down. So first thing in the morning, you go out and you try to dribble, and it just fall. We're like, what? You know, when you're young, you have literally no idea. So my cousin runs into his dad and goes, Dad, some jerk let the air out of our ball. And I'm sure he laughed about that. So he's like, yeah, somebody's just going to come along and go, hey, let's just, first off, they got a needle. Let's just let the air out of their ball, you know. And he taught us a valuable lesson. I've never forgotten that. Okay, so yeah, just understand, gas pressure is very dependent on heat. Okay, the warmer it is, the higher the pressure. The colder it is, the less the pressure. Okay, and that's pretty much universal. Okay, with every gas there is. What we are going to learn is we will get into a whole bunch of equations. Okay, we're going to start on it a little bit today, but then next time we will get into this a little more. Now, while I'm thinking about this, okay, before I forget, remember on Friday, what are we going to do? We're going to finish that lab. So I'm going to teach for like the first half hour or so, and then I'm going to give you the last half hour to finish that lab. If you are not going to get done with the lab, you need to come in today or tomorrow after school and try to finish that. Okay, I need to try to get that down so I can get the next one set up. Okay, if you did not turn your lab 6 in, it needs to get in that basket today. Okay, because then I got to get all them scored, because then I got to get 11 handed in, and yeah, my break's not going to be near as fun as yours is, I guess. Okay. Alrighty, so are you guys just not wrestling tonight? Did their whole team get quarantined?
I don't know. I think that's all the good kids got quarantined, so they're just like not
All the boys are from Layton?
Yeah.
Yeah, because I know the girls. Right?
Well, just the girls, but
Yeah,
the
just
boys
the
all
girls.
got. Was it probably just their studs? Like, yeah, we don't want to get beat again. Okay, sorry, I just had to ask. Alrighty, now, a couple of equations you are going to need. Is everyone know the equation for pressure? Pressure is equal to nobody. Yo,
Force divided by area.
force divided by area. Somebody did the Learn Smart, right? Yeah, like 7 of you is all. You see how I'm making eye contact with you? Yeah, it's probably not a good thing. Probably not a good thing. Okay. All right. So yeah, pressure is force divided by area. Nothing huge here. They will abbreviate. Capital F is force. Big A is area. Nothing revolutionary there. Okay. Now, we are going to get into some laws, and I am not a huge name guy, okay, but there are some laws you need to know by name, okay. So the first big law we're going to talk about is known as Boyle's Law, okay. Now, I'm not a big chemistry history guy. I'm not, okay, but I'm going to assume this is named after some dude whose last name was Boyle. I mean, that's logical, right? Okay, one day they might have Denton's Law. That would be freaking awesome. I mean, think about that for a second. For the rest of time, people are saying, yeah, well, then there's Denton's Law. It would be something stupid, like, I do something, my wife yells at me. I do something else, my wife yells at me again. I don't know. But yeah, we got Boyle's Law here. Now, Boyle's Law is this. PV equals K. Now, what you need to understand is this. Is that when they write K like this, K just means some constant. Just some value. Doesn't matter what it is. But I need to understand how pressure and volume are related. Okay? Now, the other thing you need to understand is that Boyle's Law only applies in it applies under specific conditions. Okay? And this is if I have constant temperature, because we already said that temperature does what? Really changes the gas, right? So it's under a constant temp, and it has a fixed little n. Whoa, excuse me. Little n. Little n stands for number of moles. Who's it for?
Hannah Hatch.
Right there. Thank you. Okay. Now, N stands for number of moles. We'll get into this probably next time. Now, PV equals K. Now, pressure and volume have a very specific relationship. They are on the same side of the equal sign. Okay, it's like in our last equations, anything that was on the same side of the equilibrium sign did what? Anybody remember when we were changing? Yeah, it did what? Opposites. Anybody remember what I said, what kind of relationship that was? An inverse, right? So, as my pressure goes up, my volume is going to go down. Okay? Now, when it says constant temp and fixed number of moles, what they're talking about is this. Okay? What I have is I have a sealed container. Okay? Which means once this is sealed, the number of moles that are in this container are not going to what? They're not going to change because it's sealed, right? We're at room temperature, so my temperature is not going to change, right? But if I take my volume and I start making the volume go down, what did I just do to the pressure inside there? It increased a lot. You guys have all played that game, right? Right? So yeah, I'm not going to do that. I can tell you guys all, I'm not going to do that. But understand that that is immensely pressurized now. Change my volume back. Right? You see what I'm saying? So yeah, so understand that no matter what, in a sealed container, at a constant temperature, pressure and volume are inverse related. Now, what if I were to take this and put it in the microwave and heat it up? What would it do? Yeah, it would expand and expand until it blew up. Okay? But the same idea. Pressure and volume, inversely related. Okay? That is called Boyle's Law. Boyle's Law. And what I would do is I would literally write on my 3x5, Boyle's Law, I would write that. Yes.
So K is always going to be the same number.
Well, no. K just means it doesn't change for the given set of circumstances.
Okay.
Meaning that if this is 12, right? And this is 6, that has to be 2, right? Well, if that's 3, that has to be 4. You see what I'm saying? K is just some value. It doesn't matter. It just means that because these are on the same side, they are going to be inversely related. Okay? Now, this should be easy because we are all at a high enough math level. Do you know what I'm saying? Okay, so the first few of these are really simple. Now, from Boyle's, we go to a dude named Charles. Okay, this is Charles's law. Okay, now Charles's law is a little different because now at Charles's law, you have a fixed N. So again, the amount of gas is fixed, right? But now I am going to have constant pressure. Okay? Constant pressure. And what you'll notice is this. V over T equals K. Now there's no P in this equation. There's no P because it already said my pressure can't change. Now, what is different about the relationship of volume and temperature compared to the relationship of pressure and volume? They're still on the same side, right? But what's different? They are. One's in the numerator, one's in the denominator, right? So for this value not to change, if my V goes up, what does my T have to do? It has to go down, go up, has to go up as well, right? This is what is referred to as a direct relation. Okay? One goes up, the other one goes up. Okay, so if this is 6, and that is 3, and my volume goes up to 12, my temperature has to go up to 6 to maintain that same value, right? And you'll notice that if this was a balloon, right? I've got that balloon tied off, which means the number of moles of gas I have in there is fixed, right? And I heat that balloon up, what's it going to do? It's going to get bigger. I cool that balloon down, it's going to get smaller. I'm sure you've all gone to the fair or whatever and gotten a balloon, right? The next morning, instead of floating in the air, it's mid-range, right? And then it goes and it goes and it goes and it goes because as it cools down, it falls. Now, they also lose air, okay? Now, there's a reason I didn't throw these away. Now, look. You go back to this Mylar balloon my stupid wife got me, okay? Now, initially, these were all doing what? They were floating in the air, right? Well, nobody popped them. They're still sealed up. Why aren't they floating in the air anymore? Well, initially, they weren't floating in the air because at night, what do they do to the heat in the building? They turn it down, right? So it got colder. So then the next day it was floating about here, right? But clearly, what has happened? Yeah, the helium was small enough that it was able to fit through all the small little holes in here. It's kind of crazy. Now, it's weird because the balloons are still... Oh, that's attached. Okay? Clearly, some of that gas had to what? It had to leave. So it doesn't obey this because it's no longer a fixed what? A fixed number of molecules, right? They've left. But if I were to take this and I were to heat it up, it would expand. If I were to put it in the fridge and cool it down, it would actually contract a little bit. Okay? That's kind of interesting. But yeah, that's what's going on there. Okay, and this is Charles's law. Again, I think this is really straightforward. Should not cause us a ton of grief on a simple equation like that. Okay? Alrighty, from there, we're going to cover one more. And that is one more page. And that is called... yeah, let's do it. Alright, so this is called Guy-Lussac's law. Guy... L-U-S-S-A-C-S. I always spell that wrong. Guy-Lussac's law. Okay? This is actually two guys. One who's... And it said Guy. It's spelled gay, but it said Guy. Guy-Lussac's law. And this is a fixed end. This is when you have a fixed end. You have constant volume. Yeah, that's it for now. And then what you're going to have is this. You're going to have P over T equals K. Okay, and we've already basically talked about this, right? And this is what I alluded to this earlier, is that pressure and temperature are directly proportional. Meaning if my temperature goes up, my pressure must go where? It must go up, okay? They are, again, these are a direct relation. One goes up, the other one goes up. Temperature goes down, pressure goes down, okay? Again, there are none, I mean, I look at these three equations, I mean, there is nothing there that is going to, that should give you any problem. And really the thing you need to understand is that just that, you know, this one doesn't involve T. This one doesn't involve P. This one doesn't involve V. So they're all just different applications of the same idea, okay? And what they end up doing is they come up with what is known as the combined gas law. Okay, and this is probably the most important law we're going to, well, the second most important law we're going to talk about, and it looks like this. P1 V1 over T1 equals P2 V2 over T2. Now, the combined gas law. Now, actually, I need to change one thing. Temperatures. Anybody remember what temperatures should be measured in? Kelvin. Temperature in Kelvin. Temperature in Kelvin. Temperature in Kelvin. I would always, from now on, go to Kelvin. You do them in Celsius or Fahrenheit, you're going to get them wrong pretty much every time. Okay, go to Kelvin, you'll be good. Now, in this situation, okay, what they're going to do is they're going to say, okay, here is basically an equation, right? in this equation, I have 6 variables, right? Well, does anybody know the laws of algebra? That if I want to solve this, what has to happen? Nobody? Not a soul knows the laws of algebra. Criddle.
Are you talking about like how the denominators have to be the same?
No, but that actually in this situation they probably will not be the same. Okay, nobody knows that if I've got 6 variables, what they have to do for me to find one of them, they got to give you 5 of them. Because I can only have one true unknown to solve this equation. If I had 2, can I solve it? No. So what they're going to do is they're literally going to say, okay, given all this information, they're going to write a paragraph. You're going to have to take that information, you're going to have to extract it, and you're going to have to do what? Film a Glade commercial? What was that look for? There's a word for that. It's called, I heard it, substitute. You've never seen the Glade commercial. Back in the day, there was this whole ad campaign, plug it in. Nobody knows the Glade plug-ins commercial? They were these stupid, and they had this little jingle, and they went, plug it in, plug it in, plug it in. No, you don't know what I'm talking about? So anytime someone says that, I think that. Because we use math terms in here, and it's called substitute. Yeah, so I'm going to extract them out. I'm going to substitute them into this equation, then I'm going to do the math. The math should be easy. The part we screw up is we put it in the wrong place, we don't use the right units or whatever. Now, pressure. Pressure is typically in what? Anybody know? Atmospheres. Volume is usually in, anybody? Liters. Temperature is obviously, I already told you, in Kelvin. Okay? Now, typically, P is in liters. Sorry, P is in atmospheres. Volume is in liters. Temperature is in Kelvin. And I would just always get used to that. Okay? They will have you do some converting. Excuse me, but none of that stuff is going to be overly complicated. Okay? Now, what they are going to do, though, is they are going to give you basically this. And this is actually a really good little cheat sheet to have. Okay? Now, right here. Okay? The summary of the gas laws, right here. Now, what they've done is if I look at like this one, look at Charles's law, okay? Before we had V over T equals what? We had a K there, right? Now, what they're doing is they're taking a situation, they're saying, okay, in this bottle, right, volume over temperature. If I heated this bottle up, its volume would do what? It would increase, right? I cool it down, its volume is going to decrease. And what they're doing is they're saying, okay, given one situation, what will happen if I change it? Okay? So, again, there's 4 variables here. What are they going to do? They're going to give you 3. 4 variables here. What are they going to do? Give you 3. 6 variables here, they're going to give you 5. All the same stuff. They just tweak one thing or tweak another. Okay? This should, and I stress should, be easy as far as that goes. Put the number in the right units. Make sure it's in atmospheres or whatever, right? Make sure it's in liters. Put it in the right place. And then do the math correctly. You do those 3 things, you should always get the right answer. Does that make sense? Okay. Now, from there, last section they're going to talk about is what's called Avogadro's law. Avogadro's law, obviously named after Avogadro, right? And that is V over N equals K. Volume, V is volume. Again, what is N?
Number of moles.
Number of moles. Now it makes sense that the more moles I have, the more what? More volume I'm going to have, right? If I put 1 mole in a balloon, it's going to have half as much volume as if I put 2 moles, right? No matter what, I put more in there, its volume's got to increase, okay? So again, just another situation. They will tweak this, and they will go V1 over N1 equals V2 over N2. And usually this is like an initial, and this is like a final. But they will word it a couple of different ways just to try to confuse you. And for about half of you, it will work, okay? But there's really nothing rocket scientific here about this stuff, especially these early equations. Once we get into like the ideal gas law, which is perv nerd, it does get a little higher level, but nothing overly complicated here, okay? So let's say I gave you this. So let's say I said given a container with a P of 6 ATMs and a V of 14.7 liters. Let's go 6.0 ATMs and a volume of 14.7 liters at 28 degrees Celsius, right? And I cool it to negative 15 degrees Celsius. What will be the new pressure? Okay. Given a, let's go put sealed right here. So given a sealed container with a pressure of 6.0 atmospheres and a volume of 14.7 liters at 28 degrees Celsius, and I cool it to negative 15 degrees Celsius, what will be the new pressure? Okay, so look at this. So you got P1, V1 over T1 equals P2, V2 over T2, right? Now, the combined gas law, like, always works, assuming you do it correctly. Now, I've got to take this, I've got to extract that data, and I've got to put it into this equation. Okay? So I always use my 1 as where I start at. So what's my initial pressure? 6.0 ATMs, right? What's my initial volume? 14.7 liters, right? What's my initial temperature? What? I taught that already, didn't I? 3 what? 301? 301 Kelvin? Anybody remember that? How'd you get that? Celsius plus 273. Is she right? Number is she the only one that remembers that? What's the matter, Criddle?
I didn't think it was that easy. I thought it was like this big.
Okay, that's if I'm going where? You're thinking Fahrenheit to Kelvin.
Okay, yeah.
Hannah, did you have a question?
Well, are you adding from 28?
Yeah, so don't I go 273 plus 28, right? Okay. And then that's going to equal, what's my P2? Yeah, that's what I'm what? That's what I'm looking for, right? So I got P2. What's my new volume? Yeah, so if it doesn't change or doesn't address it, it must be the same, right? So that would be my 14.7 liters. And then my new T is what? What? 258? Like that? Now, I have a question. Did I have to use this equation? Anybody know? Why not?
The only thing that changed was temperature, and then you're looking for pressure.
Okay, so here's the thing you need to understand is that this equation always works. As long as I realize, as Richard pointed out, my volume didn't change. Well, my volume didn't change. Did I really need it? I didn't. So sometimes they'll put in extra information, right? Is there another equation I could have used that puts just what I need and just what changes together? Yeah, what would it have been?
The Guy's law.
Yeah, what's it?
P divided by T equals 10.
P1 over T1, but for this one, it's going to have to be P1 over T1 equals P2 over T2. What you'll notice is that if I look at this and I divided my liters out, they'd be gone anyway, wouldn't they? Wouldn't that end up as P over T equals P over T? Now, what I used to do is I would say, well, if I know this really takes into account all those other laws, right? And then I just eliminate what's not what. What doesn't change. Does that make sense? And then it kind of helps me keep my mind a little less cluttered because I got 50 years of crap in there and half of it I don't need anymore. Okay? So, how am I going to solve that? I forgot again. Man, you think I'd remember that it's a short day. When I just times by 258 Kelvin, times by 258K, times by 258K, right? Because we already got rid of our liters, correct? That's going to give me a P2 equal to what? Have I not mentioned that we should have a calculator out and be using it every day in this class? I'm pretty sure we could probably go back and check the video. You're welcome. Okay. What? Do you have it? No? What do you got, Garrett?
I said 76.
76? That would be 76 what?
Atmospheres.
Atmospheres? Okay, what? Now look. This is something that I don't think I'm picking on you. Okay? Now, this is something that I'm going to be honest, students drive me nuts with. Okay, and I'll tell you this story, not today because we're running out of time. When I get this answer, I need to say to myself, so, could that answer be right? Now, myself, because I'm the teacher, I looked at this, and the minute he said that, I knew he had to be what? Why? Why did I know that? Because my temperature went down. And I know that pressure and temperature are directly related, right? So I know my pressure must also go down. Does that make sense? So look at that. And this is something you'll see on the test a bunch. Look at that answer and say to myself, Garrett, could that be right? It can't be. Because this value has to be less than this value. Because that value is less than that value. Because that value didn't change. Does that make sense?
Yeah.
Okay. So, do you have it?
Yeah.
Fish, what do you got? 5 point. Anybody else get 5.1? Okay. I have no idea. Do you see what you did?
No idea.
Me neither.
That's what I got too.
You got the same thing? I have no idea how you got that.
Yeah, it's 258 and 6 and 14.7 multiplied all together, right?
No, that's what's wrong. That's what's wrong. Why did we not use our 14.7? Because we pointed out that it didn't change. Does that? Okay, I was like, where are you getting? That makes sense now. Okay? And that's what you're going to run into. There's like 5 or 6 of that kind of question on the test. Okay? Alrighty. I was going to give you a few minutes to work, but clearly I forgot again. that it was late start, so I'm sorry. Hey, while I'm thinking about it, we are going to. They changed the assembly. I don't know if you guys heard that on the announcements. So we will actually be teaching next Tuesday. So those of you that had already chalked next Tuesday up to being not here, none of you nobody had already had that thought. Yeah, okay, thank you, Carol. I will actually be teaching that day, so I would highly recommend you come. Okay, simply because when it was going to be a wasted day, it wasn't going to be a big deal. But now they moved the assembly back till after, which doesn't make any sense. I don't get, but I'm not in charge, so whatever. We will be teaching, so I would plan on being here on Tuesday, right? Because that is this day, right?
Yes.
It's a B day. We'll all be here. So if not, though, are you guys still there? I don't know. They were there, right? There were people there, like she was there, right? Okay, so whatever. So yeah, just plan on being here because I am going to teach. And then what we'll do is I built an extra day in for after to kind of get back from the. You guys all know how the day you come back, you're like, oh, we're in school. You actually, who are you? Come on. Okay, get out of here. I know you know what I'm talking about.